Section 2.5 is going to take on the topic of transformations of functions. Below, you're going to see an excerpt from your text, and it includes 7 of the most common functions that you may encounter in a mathematics class. You can think of them as being parent functions for a whole host of other more complicated functions. And the key is going to be that if we know these parent functions well and understand how some basic transformations will affect their graphs, then we will be able to sketch the graphs of more complicated functions easily and quickly. So let's just take a quick look at these algebra's common graphs, is how our textbook refers to them. I call them the parent functions. And we're not going to spend too much time talking about the constant function. It's not very interesting, and in fact, we're not going to do much with it at all. We will talk about the identity function, though. That's basically y equals x, and you can see the points on the graph are a reflection of that equation. If x is 0, y is 0. If x is 1, y is 1. If x is 2, y is 2. If x is negative 1, y is negative 1. So f of x equals x, or y equals x, is the identity function, and it's a line that goes through the origin. Its domain is all real numbers, its range is all real numbers, and it is increasing on its whole domain. And if we look at the graph and we ask what kind of symmetry it has, if we put a pin in the origin and turned it through 180 degrees, it would exactly match itself. So this is an odd function. Now, the next one we're going to think about is the absolute value function. F of x, or y, equals the absolute value of x. 0, absolute value of 0 is 0. The absolute value of 1 is 1. The absolute value of negative 1 is 1. The absolute value of 2 is 2. The absolute value of negative 2 is 2. So we get this basically V shape, right, that is decreasing until it reaches the origin, and then it begins to increase, right? Its domain is, of course, all real numbers. Its range is from 0 to positive infinity. It is decreasing from negative infinity to 0. And remember, these are always open intervals, right? And it's increasing on the open interval from 0 to positive infinity. And if we think about the symmetry that the absolute value function has, it's symmetric about the y-axis, and so the absolute value function is even. Now, the next one we're going to think about is the standard quadratic function. F of x equals x squared, or y equals x squared. And we can see that the points that will appear on this graph, 0 squared is 0, 1 squared is 1, 2 squared is 4, negative 1 squared is 1, negative 2 squared is 4, right? So this is a U shape. And its domain is, of course, all real numbers. Its range is from 0 to positive infinity. It's decreasing on the open interval from negative infinity to 0, and increasing on the open interval from 0 to positive infinity. Because it's symmetric with respect to the y-axis, this is an even function. So now we're going to look at the square root function, the parent square root function. F of x equals the square root of x, or y equals the square root of x. And because we want our function to return real values for the inputs, the least value of x that we can use for the domain is 0. Because if I went less than 0, I would be taking the square root of a negative number, and the result of that, of course, is an imaginary number. So our domain is going to begin at 0 and go towards positive infinity, right? The square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. So it has this basic eyebrow shape, right? Again, the domain is from 0 to positive infinity. The range is also from 0 to positive infinity. We're looking at the positive square root of x, so only from 0 to positive infinity will be in the range. It is increasing on the open interval from 0 to positive infinity. And because it doesn't have symmetry with respect to either the y-axis or the origin, this function is neither even nor odd, and it's the only one of the parent functions that is neither even nor odd. The last two we're going to think about are the standard cubic and the cube root function. And the standard cubic function is f of x equals x cubed, or y equals x cubed. The domain is going to be all real numbers. The range is also all real numbers. And I can see the basic shape that this will make if I think about whatever the value of the independent variable or x is, I'm going to cube it. So 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, negative 1 cubed is negative 1, and negative 2 cubed is negative 8. So it has this basic shape. It is increasing on its entire domain. As I read from left to right, my pen is always going up. And if I put a pin, P-I-N, in the origin and turned it through 180 degrees, it would match perfectly. So this is an example of an odd function. And the last of the parent functions is the cube root function. F of x, or y, equals the cube root of x. Again, the domain and range are both going to be all real numbers, and its basic shape is going to be a consequence of the fact that I'm going to take the cube root of whatever that input is. The cube root of 0 is 0. The cube root of 1 is 1, because 1 times 1 times 1 is 1. And then the next number that has a nice cube root would be 8, right? The cube root of 8 is 2, because 2 times 2 times 2 is 8, so that would be up here, right? So it's going to be looking like this. The cube root of negative 1 is negative 1, because negative 1 times negative 1 times negative 1 is negative 1. And then the next integer that has a nice cube root is negative 8, because negative 2 times negative 2 times negative 2 is negative 8, so that would be somewhere around here, right? So the cube root function has this basic shape. And again, the domain and range are both all real numbers. This function is also increasing on its entire domain. As I read from left to right, my pen is always going up. It's rising from left to right. And again, I'm looking at an odd function, because if I put a pen, P-I-N, in the origin and turned it through 180 degrees, it would match itself perfectly. So those are the 6 basic parent functions that you're going to need to be able to think about the next part of the section, and that's transformations that are going to be carried out on these basic parent functions. So before we're going to be able to do transformations on these, we need to make sure that we have these well established. So if you need to, if these are new to you, go ahead and pause the video and take a minute to make sure that you understand both the function definition for each of these parent functions, as well as their basic graphs and their shapes. Okay, so in this example, we're going to be using transformations to graph the following functions. And we're going to establish what these transformations are going to be with the following 2 examples. The first example is f of x equals x squared plus 4. And then for part B, f of x equals x squared minus 2. But in both of these functions, the parent function is the quadratic, or y equals x squared. That's going to be the parent function there. And I'm going to go ahead and I'm going to sketch the parent function in blue on both of these graphs. So I know it's 0, 0, 1, 1, 2, 4, negative 1, negative 1, negative 2, 4. If I wanted, I could do 3, 9, and negative 3, 9, right? I'm going to do it with a dotted line. And then I'm going to come over here and I'm going to sketch that same parent function. 1, 2, 4, and then 3, 9. Now, I'm going to go ahead and I'm going to graph f of x equals x squared plus 4 by making a t-chart. And I'm only going to do this one time for each example, just to establish what this transformation is going to look like. And then after that, I'm going to be able to use that information in order to more quickly create the graph of a transformation of one of my parent functions. So when I was graphing my parent function in blue, the values that I used for x were -3, -2, -1, 0, 1, 2, and 3. And -3 squared is 9, -2 squared is 4, -1 squared is 1, and then 0, 1, 4, and 9, right? So I'm going to use the same x values over here. -3, -2, -1, 0, 1, 2, and 3. And I'm going to see what the effect is going to be when I graph x squared plus 4. So now looking over here, what am I finding the points for? F of x equals x squared plus 4, right? So -3 squared is 9, plus 4 is 13. -2 squared is 4, plus 4 is 8. -1 squared is 1, plus 4 is 5. 0 squared is 0, plus 4 is 4. 1 squared is 1, plus 4 is 5. 2 squared is 4, plus 4 is 8. 3 squared is 9, plus 4 is 13. And so I'm going to go ahead and plot those points. -3, 13 is not on my graph, but -2, 8 is. And then -1, 5. And then 0, 4. And then 1, 5. And then 2, 8. And then, of course, 3, 13 is off the graph. So I can go ahead and connect these points to make my parabola, right? And I can see that the effect of adding 4 to my parent quadratic function is to take the graph of that parent function and do what? Shift it up 4 units. Every point with the same x value, right, was shifted up 4 units in the positive y direction, right? So in other words, if I could take this, right, and pick it up, and I could just slide it right up here 4 units up. I can see that reflected in my ordered pairs, right? The same x values, each y value was greater by 4, shifted up 4 units. Now, let's go ahead and look at the second one. So this one is going to be f of x equals x squared minus 2. So I'm going to go ahead and I'm going to make a t-chart here. And I'm going to use the same -3, -2, -1, 0, 1, 2, and 3. And then I'm going to see what the effect of subtracting 2 from each of those squared values is going to be. So -3 squared is 9. 9 minus 2 is 7. -2 squared is 4, and 4 minus 2 is 2. -1 squared is 1, minus 2 is -1. 0 squared is 0, minus 2 is -2. 1 squared minus 2 is -1. 2 squared, 4 minus 2 is 2. 3 squared, 9 minus 2 is 7. So let me go ahead and plot those points. So -3, 7. -2, 2. -1, -1, 0, -2, 1, -1, 2, 2, and 3, 7. And when I connect these in a nice parabola, I see that the effect on my parent function of subtracting 2 was to shift the entire graph down 2 units. So I can see each point is shifted down 2, right? Down 2, down 2, down 2, down 2, down 2. If I add a constant to my parent function, it's going to shift it up that number of units. And if I subtract a constant from my parent function, it's going to shift it down that number of units. But it's not going to change the shape of that parent quadratic, right? These are referred to as rigid transformations. I'm not changing the shape of the parent. I'm just either moving it vertically up or vertically down. The domain for the transformed function over here on the left, x squared plus 4, is still -infinity to +infinity, but the range is going to be from 4 to positive infinity because everything was shifted up 4 units, right? Over here, my domain remains unchanged, but my range is shifted down to -2 to positive infinity, right? So what can we take away from these two examples? We're looking at vertical shifts or translations, and if we let f be a function and c a positive real number, then the graph of y equals f of x plus c is a graph of y equals f of x shifted up c units. And the graph of y equals f of x minus c is a graph of y equals f of x shifted down c units. So that is our first transformation, a vertical shift or translation. So let's look at a couple more examples. And let's look at f of x equals the absolute value of x plus 2. Because we're not going to make a t-chart every time we want to graph one of these transformed functions, right? The whole idea is to use the power of that pattern that we just observed in order to make easier work of this. So the parent function for this particular one will be y equals the absolute value of x. And the transformation that is going to take place on that parent function is going to be a shift up 2 units. So now I'm going to go ahead and I'm going to sketch in my x and y axes. And then I'm going to very lightly plot the points of that parent function. 0, 0, 1, 1, 2, 2, 3, 3. You know the basic shape that it takes, right? And then I'm going to go ahead and take each of these points and shift them up 2 units. So this point is going to shift up 2. This one's going to shift up 2, up 2, up 2, up 2. All of them are going to shift up 2 units. And so there is my function f of x equals the absolute value of x plus 2. The domain will be from negative infinity to positive infinity, and the range will be from positive 2 to infinity. And I didn't need to make a t-chart, right? I'm using the power of the pattern that I observed with respect to that kind of a transformation. Now what if I had the same function, but instead I had f of x equals the absolute value of x minus 3? Well, I would begin with the same parent function, and I'll do this one in purple so that I can tell the difference, right? Same parent function, but every one of these points, right, is now going to be shifted down 3. 1, 2, 3. 1, 2, 3. 1, 2, 3, right? So down 1, 2, 3. Down 1, 1, 2, 3. Down 1, 2, 3. Down 1, 2, 3. Down 1, 2, 3. You get the idea, right? And it's a rigid transformation. The shape of the parent function doesn't change, just its location on the plane, right? So the domain here is still all real numbers, but the range is from -3 to positive infinity, right? So again, use the power of that pattern that we've observed in order to much more quickly sketch the graphs of these transform functions. And you know, if you spend enough time with this, then you know in your mind what that basic shape is, and you don't even need to plot those points in order to know what the resulting function is going to look like. Now, the next example that we're going to look at is going to involve the square root as the parent function, right? And if you notice, this is slightly different than what we've done before. This is not the square root of x minus 5. It's the square root of the quantity x minus 5. So we're going to expect that this is going to do something different, right? And instead of the square root of x plus 3, we have the square root of the quantity x plus 3. In both cases, the parent function is y equals the square root of x. And of course, if I made a t-chart for that, it would look like 0, 1, 4, 9, because I want numbers that have nice integer square roots, right? Square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, and the square root of 9 is 3. So 0, 0, 1, 1, 4, 2, 9, 3. You can sketch that in. Same thing over here, 0, 0, 1, 1, 4, 2, 9, 3. You can sketch that in. And now I am going to go ahead and make a t-chart for f of x equals the square root of x minus 5 and see what the effect is going to be. So when I think about this, I cannot start with 0 because 0 minus 5 is going to give me negative 5, and that would end up being an imaginary outcome, and I don't want that. So the least value of x that I could plug into this expression and have 0 under the radical, right, would be 5. 5 minus 5 is 0. The square root of 0 is 0. Now I would like to have a 1 under the radical next, right? If I want a 1, then this needs to be 6. 6 minus 5 is 1. The square root of 1 is 1. The next number that I would like to see under that radical is 4. So this needs to be 9. 9 minus 5 is 4. Square root of 4 is 2. The next number I would like to see under this radical is 9. So what do? I do the opposite of subtracting 5. I add 5 to 9 and get 14, right? 14 minus 5 is 9. Square root of 9 is 3. And so when I plot these points, I see 5, 0, 6, 1, 9, 2, and of course 14, 3 would be off the graph. And I can see that the effect here is to shift the parent function, not vertically, but horizontally, right 5 units. And it may be a little confusing because I subtracted 5, right? And yet it went in the positive direction 5 units. But think about, how did we arrive at all of these points that we wanted to use as our x values? All of these numbers that we wanted to use as our x values. We wanted to end up with 0, so we had to add 5. We wanted to end up with 1, so we had to add 5. We wanted to end up with 4, so we had to add 5. We wanted to end up with 9, so we had to add 5 to each what? To each x value. Adding 5 shifts it to the right 5 units. Now let's see what happens over here when we look at graphing f of x equals the square root of x plus 3. So I'm going to make a t-chart. And I'm going to think about selecting values of x so that I will end up with nice numbers under my radical to take the square root of, right? Now over here, in order to get those nice numbers I wanted, 0, 1, 4, and 9, right? I added 5 to 0, 1, 4, and 9 in order to figure out what my x value should be. Over here, in order to be taking the square root of 0, 1, 4, and 9, instead of adding 3, I'm going to subtract 3. I'm going to do the opposite. So 0 minus 3 is negative 3. Negative 3 plus 3 is 0. Square root is 0. Next number I would like to take the square root of is 1. 1 minus 3 is negative 2. So negative 2 plus 3 is going to give me 1, the square root of which is 1. The next number I would like under that radical is 4. 4 minus 3 is 1. And then, so then that's the square root of 4, which is 2. And then the next number I'd like to take the square root of is 9. 9 minus 3 is 6, so that when I do 6 plus 3, that's going to give me 9, square root of which is 3. So now I'm going to plot these points, negative 3, 0, negative 2, 1, 1, 2, and 6, 3. And I can see that the effect in this case is to shift this transform this, a rigid transformation. It just picks it up and shifts everything to the left 3 units, right? So a good way to think about this, the way that I think about it, is I say to myself, okay, I know this is going to be horizontal transformations because it's within my parent function. And is it going to go left or right? Well, what would I need for x in order for this to be 0? A positive 5. The positive direction is to the right 5 units. I would like for this to be a 0. What would x need to be? Negative 3. So the entire thing is going to shift in the negative direction to the left 3 units. Notice that for all of these, the outputs did not change, right? So it's the domain that shifts and not the range. The domain for the function just above here, right, the red one, is going to be from 5 to positive infinity. The range does not change. It's still 0 to positive infinity. Now over here with the purple, the domain shifted to the left 3 units, but the range did not change. So what pattern have we observed through these two examples? If we let f be our function and c a positive real number, then the graph of y equals f of the quantity x plus c is going to be a shift of the graph of y equals f of x to the left c units. And the graph of y equals f of the quantity x minus c is going to be the graph of y equals f of x shifted to the right c units. And I can take that away with the pattern that I've observed. And so now I don't need to make t-charts anymore. I can use the power of that pattern in order to create my transformations of my parent functions. So another example again, to see how we're going to put this into practice. F of x equals the quantity x plus 2 squared. So my parent function here is the quadratic, right? Y equals x squared. The transformation that is going to take place is going to be a shift. Now let's think, is it going to be left or right? I would need a negative 2 to make this 0, so it's going to go left 2 units. So I'm going to go ahead and sketch my graph. So my parent function, if I need it, 0, 0, 1, 1, 2, 4, negative 1, 1, 2, 4. I'm going to take each and every one of these points and shift them left 2 units. So this one's going to move left 2 units, left 2 units, left 2 units, left 2 units, right? So left 2, left 2, left 2, left 2, left 2. And there is my transformed quadratic function. Now, the domain on this one is not going to change because it was already all real numbers, and the range is not going to change because it was a horizontal transformation. Now, what if I had instead f of x equals x minus 3 quantity squared? Again, I have the same parent function, and let's do this one in purple. Same parent function, except for now the transformation is going to be to shift, is it left or right? I need a positive 3 to make 0, so right 3 units. So I'm going to go ahead and I'm going to take each and every one of these points in my parent function and shift them right 3 units. 1, 2, 3, 1, 2, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So there's that transformation. Again, the domain on that one is all real numbers. Shifting it left and right is not going to change that. And the range is 0 to positive infinity because there was no vertical translation at all. So now that I have the power of that transformation, I can look at the last two that I'm going to be thinking about. Now, for the last two transformations that we're going to consider, we're going to have two different functions this time. The first one is going to be f of x equals the opposite of the absolute value of x, and the part B is going to be f of x equals the square root of the opposite of x. So for each of these, I'm going to begin by saying that the parent function, stating what that is, the parent function for this one is y equals the absolute value of x. And I'm going to go ahead and sketch that on here. 0, 0, 1, 1, 2, 2, right? It makes that nice V shape. And then I'm going to go ahead and I'm going to graph f of x equals the opposite of the absolute value of x by making a t-chart. And I'm going to use the same numbers that I used when I was graphing my parent function. Negative 3, negative 2, negative 1, 0, 1, 2, and 3. And then what am I going to be doing? I'm going to be taking the absolute value and then the opposite. So the absolute value of negative 3 is 3. The opposite of 3 is negative 3. The absolute value of negative 2 is 2. The opposite of 2 is negative 2. The absolute value of negative 1 is 1. The opposite of 1 is negative 1. The absolute value of 0 is 0, and the opposite of 0 is 0. The absolute value of 1 is 1. The opposite is negative 1. The absolute value of 2 is 2. The opposite is negative 2, and then negative 3, right? So if we plot these points, we're going to see exactly what happens to our parent function. It's going to be reflected over or about the x-axis, right? So the domain remained unchanged, negative infinity to positive infinity, but now the range, instead of being from 0 to positive infinity, is from negative infinity to 0, because it was reflected over the x-axis. Now let's look at the second example. And that one is f of x equals the square root of the opposite of x. And so my parent function again here, this time is the square root of x, right? And so when I'm plotting those points, which I should know well, right? 0, 0, 1, 1, 4, 2, 9, 3. If I know my parent function, this is all going to be very much easier, right? And then I'm going to graph the transformed function. F of x equals the square root of the opposite of x. Now, when I'm making my t-chart for this one, I can't use the same numbers that I used when I was plotting my parent function, right? Because I'm going to take the opposite. So I can still take the square root of 0. The opposite of 0 is 0. Square root is 0, right? But now, the next nice number that I would like to see under here is 1. Well, I need to take the opposite of 1 so that I will get 1. That's going to be negative 1. The opposite of negative 1 is 1. The square root is 1. And then I need to put what? A negative 4, because the opposite of negative 4 is positive 4. Square root of 4 is 2. And then a negative 9, because the opposite of negative 9 is 9. The square root of 9 is 3. And so I can see that when I am taking the opposite, right, of the input, right, f of negative x, instead of negative f of x, this is f of negative x, this is going to be a reflection about the y-axis, right? And so my domain is changed. It's now from negative infinity to 0, but the range remains unchanged. And the generalization or takeaway that I can make from these two examples is that a reflection about the x-axis is defined by the graph of y equals the opposite of f of x is the graph of y equals f of x reflected about the x-axis. How to think about that. And the graph of y equals f of the opposite of x is a graph of y equals f of x reflected about the y-axis. And so the generality there has to do with reflections, and it makes a difference where that negative sign is found, right? If it's the opposite of f of x, then that's going to be a reflection about the x-axis. If it's f of the opposite of x, then that's going to be a reflection about the y-axis. Now, a function can involve more than one transformation, and functions that do involve more than one transformation can be graphed by performing the transformations in the following order. First, we'll do any horizontal shifting or translation. Then we'll do any reflecting about the x or y axis. And then we'll do any vertical shifting or translation last. And if we go in this order, then the graph will end up where it needs to be. So let's look at some examples of that. So for example number 4, we're going to use transformations to graph the following function. F of x equals the square root of the quantity x plus 4 minus 2. So the first thing that I'm going to ask myself is, what is the parent function? And the parent function in this case is y equals the square root of x. The next thing that I'm going to ask myself are what transformations are going to be taking place. Well, I see that I am adding 4 to x within the square root, so I know that that is a horizontal translation, right? So this represents a horizontal translation. And then the minus 2 after my function represents a vertical translation, right? And I need to do those in the correct order. So the first thing that I'm going to do, go ahead and make note here. These are the transformations that are going to take place. First, I'm going to do any horizontal, which is going to involve that plus 4 under the radical, right? And that's going to involve a shift in which direction? Well, remember, what would make this 0 is a negative 4, so it needs to go left 4 units. And then there is no reflection going on with this particular function. So I'm going to skip to the vertical shift, and because I am subtracting 2, I'm going to shift down 2 units. So let's go over here, and once you get more comfortable and familiar with this, you might not need these intervening steps, but I'm going to go ahead and show them. I'm going to put my parent function on their very light dotted line, 0, 0, 1, 1, 4, 2, 9, 3. The first thing I'm going to do is I'm going to take each of these points and shift them left 4 units. So left 4 units, 1, 2, 3, 4. This point is now going to be here. This point, 1, 2, 3, 4, is now going to be here, right? And because this is a rigid transformation, the square root function is going to maintain its same basic shape, right? 2, 3, 4. Still dotted line because I'm not to the end result yet, right? And then these go in order, right? The next thing I'm going to do is shift all of these points down 2 units. So down 2, down 2, down 2, down 2. Down 2, down 2, down 2, down 2. And I'm going to go ahead and draw this in because this is the final result, right, of the series of transformations that took place. So I began with my parent function, square root of x. I shifted left 4 units, and then I shifted down 2 units to end with this result. So this is the graph of f of x equals the square root of x plus 4 minus 2. The domain of this particular function is going to be from negative 4 to positive infinity. And the range, remember that's the y values, is going to be from negative 2 to positive infinity. And so, just knowing that basic shape of my parent function and these rigid transformations, I was able to very quickly arrive at my graph. Now, my next example is f of x equals the opposite of the absolute value of x plus 3. I'm going to go through that same set of steps by first asking what is my parent function, and in this case that's y equals the absolute value of x, and then what transformations are going to be taking place. Well, I'm not going to have any horizontal translation, right, because I just have the absolute value of x. I am going to have a reflection over the x-axis, and I'm going to have a vertical shift up 3 units. So in this case, it's important that I do those in the right order so that it will end up in the right place. I do horizontal, reflect, and then vertical. So the first thing I'm going to do is my reflection of my parent function over the x-axis. And then I'm going to do my vertical transformation, which is going to be a shift up 3 units. Okay, so first, second. So I'm going to go ahead and sketch in my absolute value function. You may get to the point where you don't need to do this first. It's fine. You don't have to. The first thing I'm going to think about, though, is reflecting this over the x-axis. So this point at negative 2, 2 is now going to be at negative 2, negative 2, right? Everything just gets flipped. Whoop! Put that one on the wrong spot. Everything just gets flipped right over that x-axis. So this point that was here at 2, 2 is now at 2, negative 2. This point that was at 3, 3 is now at 3, negative 3, right? So all of these points are reflected over that x-axis. And then the last thing that I'm going to do is I'm going to shift the whole thing, this, up 3 units. So this is going to shift up 3, right? So up 3. And this is a rigid transformation, right? So the shape is not going to change. And there's the result, the end result. It's the graph of f of x equals the opposite of the absolute value of x plus 3. The domain is not going to change for this one. It's going to be from negative infinity to positive infinity. But the range is going to change because it was reflected, right? And shifted. So from negative infinity up to and including 3. And we have completed that graph using our transformations that we developed and using those patterns that are really, again, it's a very powerful method to be able to graph a whole lot of these really common functions. So now let's look at this last example, and we're going to use transformations to graph the following function. f of x equals the opposite of x plus 3 squared plus 4. So my parent function is my quadratic. Y equals x squared. And if you remember from our discussion in section 3.1, this looks very much like standard form. Standard form is f of x equals a times x minus h squared plus k. We'll come back to that in a minute, all right? So now let's just go ahead with what we've been doing so far. My parent function is the quadratic. I notice that I'm going to have all three of my transformations, right? Here, I'm going to have a horizontal translation, I'm going to have a reflection, and I'm going to have a vertical translation as well. I know they go in the order horizontal, reflect, then vertical, right? So the first thing that I'm going to do is I am going to carry out my horizontal translation, and the question is it going to go left or right? I need a -3 to make this 0, so that means it needs to go to the left 3 units. Then I'm going to carry out my reflection about the x-axis. And then finally, I'm going to shift up 4 units because I am adding 4. So now you can put as much or as little of the frameworks, right, the scaffolding to get to the end result as you need. I'm going to go ahead and show all of it. I'm just going to do a dotted line again because I'm not finished. And then I'm going to shift all of these points to the left 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3, right? 1, 2, 3. 1, 2, 1, 2, 3. Again, still a dotted line because I haven't ended at my result yet. The next thing I'm going to do is reflect all of these points about the x-axis. So this point, which was at -6, 9, is now going to be at -6, -9, right? The equal distance on the opposite side of that x-axis. This is going to shift to -4. This is going to shift to -1. This is going. I'm supposed to be using red. Yeah, chirp, chirp. That's going to stay where it is. Shift. Going to be at -4 and -9. So there we are now. And then finally, we're going to shift the whole thing up 4 units. So all of these points are going to shift up 4. So 1, 2, 3, 4. 1, 2, 3, 4. 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And there is the end result, and it is a graph of f of x equals -x plus 3 squared plus 4. The domain is all real numbers. The range is going to be from -infinity up to 4, because this doesn't have a least value, it has a greatest value of 4. Okay, so now I want to talk a little bit about this standard form. All right, and when I have a quadratic function written in standard form, The A is still telling me whether the function opens up or down. And because I had a negative in front, that told me that this function, this quadratic, this parabola was going to open down, right? Now the H and the K, let's look at what the function was written out to be, right? It was f of x equals negative x plus 3 squared plus 4. Now, what I want you to do is think about where the vertex is on this parabola. The vertex on this parabola is at negative 3, 4, right? So my vertex is at negative 3, 4. And if I have a parabola or quadratic function that's written in standard form, then this is a really easy form for me to be able to find the coordinates of the vertex because they're going to be at h, k. The vertex, if it is in standard form, will be at h, comma, k. Now think about this for a minute. It's x minus h, right? So if I wanted this to be in the form x minus h, it would have to look like x minus negative 3, right? And so my vertex is at negative 3, 4. Why is it ending up there? Well, in order for me to think about that original point where the vertex was 0, 0, right? I would need for this to be 0. Well, I need a negative 3, right? So it's going to shift left 3. And then plus 4, it's going to shift up 4. So my vertex is going to end up at negative 3, 4 at h, k. Okay, so now in the homework, you're also going to have a couple of problems that have to do with just general functions that have been transformed. It doesn't have to be a parent function. I can take this kind of a weird looking W shape, which would be a function because it would pass a vertical line test, right? And I can think about transformations of this graph in order to graph g of x, which is the opposite of f of x. And remember, what does that do? That is a reflection of the graph of f of x about what? The x-axis. So I can go ahead and plot the points on my transformed function. It was here at positive 5. Now it's going to be at negative 4, negative 5. This point was at negative 2, positive 1. Now it's going to be at negative 2, negative 1. This is on the x-axis. This is going to end up down here at negative 2. This is going to be at negative 1. And this is going to be at negative 4. And so I can connect my points. And there is the transformation of that particular function. Now, what's going to happen with that same function y equals f of x if we transform it by saying that g of x is going to be equal to f of x minus 3 minus 2. Well, this is going to be a horizontal translation. To make this 0, it would be a positive 3 units to the right. So we're going to go 3 right. And then we're going to go down 2. Right? No translation, no reflections this time. And I'm just going to go ahead and take each point and do the do both transformations on each point. So this one is going to go 3 to the right, 1, 2, 3 to the right, and down 2. So he's going to end up right here. This point is going to go 3 to the right, 1, 2, 3, and down 2, so it's going to end up right there. There. This point is going to go 3 to the right and down 2. 1, 2, 3, and down 2 right here. Down 2. So let's start sketching this together. It's going to look like this. so far, right? Now, this point is going to go 3 to the right. 1, 2, 3, and down 2. It's going to end up right there. This point is going to go 3 to the right and down 2. It's going to end up right there. So we can connect those. And then finally, this point is going to move 3 to the right and down 2. So 1, 2, 3, down 2, right here. And there is the graph of g of x, which resulted from two transformations of my function f of x. Everything moved right 3 and down 2. So now I'm going to show you a couple of examples from the homework, so you'll see how you're going to navigate my math lab with these types of questions. Notice that with this one, we're looking at use transformations of f of x equals x squared. So my parent function is the quadratic to graph the following function, g of x equals x squared plus 3. So I'm going to go ahead and start the video. Again, reading the directions, f of x equals x squared to graph the following function, g of x equals x squared plus 3. This is going to be a parent function of the quadratic, and it's going to shift up 3 units. So I'm going to click on the graph to enlarge it. And you see it says click the graph and choose a tool in the palette and follow the instructions to create your graph. And I'm going to want to use the x squared tool. And this is kind of different than what we've done before. You just click anywhere on the graph, and it's going to plot that parent quadratic for you. Now, we know that we want to shift it up 3 units, and it varies with respect to the problems, but there's never going to be any stretching or shrinking, so you can ignore that part. We have a vertical shift up 3 units, so you're going to go ahead and put a positive 3. There's no reflections, and then hit enter. And it's going to shift that parent function right up there for you up 3 units. Then you're going to click save and check your answer. And we have gotten that one correct, right? So it's my parent function shifted up 3 units. Now, there's also going to be some multiple choice questions as well. So let's look at that. This one says, begin by graphing the absolute value function, f of x equals the absolute value of x as your parent, and then use transformations of this graph to graph the given function, h of x equals the absolute value of x minus 6. What transformations are needed in order to obtain a graph h of x from the graph of f of x? Select all that apply. Well, this is going to be a vertical translation down 6 units, right? And that's the only one. So I'd say it says great. And then it's going to give me a multiple choice lineup, and I'm going to find the one that represents the parent absolute value function shifted down 6 units, and that's going to be B. This one, the one A is shifted to the right, C is shifted to the left, D is shifted up, B is the one I want. And great, right? So nothing too terribly difficult about these homework problems, right? Now, this one is a little bit different. It has more transformations, so I wanted to show you what this one's going to look like. So I'm using transformations of my parent quadratic to graph the given function. And what's going to be going on there is I'm going to be shifting it, reflecting it, and shifting it to the right 2 units, right? So I'm going to click to enlarge the graph. I'm going to choose my x squared tool and click anywhere on the graph. And then there's going to be a horizontal reflection 2 units to the right. What would x have to be to make 0? Positive 2. So it's going to be 2 units to the right. And then I'm going to reflect it over the x-axis. So horizontal shift, positive 2 units, and then a reflection over the x-axis. And as soon as I do that, it carries that out for me. Save and check. And excellent, right? So, as long as you know what the transformations are going to be, the homework is going to make it pretty simple to generate the transformed graph. Just a couple more examples. This one is parent function is the absolute value. And then you're going to use transformations of this graph to obtain the given function. What's going on here? Well, it looks like we're going to have a horizontal transformation 1 unit to the left, a reflection over the x-axis, and a shift down 2 units. So we have a reflection about the x-axis, we have a vertical translation, and a horizontal translation. And then I'm going to pick it from the lineup. I know that it needs to shift to the left 1 unit, reflect, and then move down 2 units. And if it's kind of small, I can blow it up so I can see it better. Shifts to the right, to the left 1 unit, reflects, and shifts down. There we go. One more video. This one's because it looks a little different. So I'm going to be graphing my parent cubic. I'm going to shift it to the left 5 and down 7. I'm going to pick my cubic tool, and then I need to shift it to the left 5 units. Now this one uses these little slider bars. So I'm going to shift it to the left 5 and then down 7, vertical shift down 7 using a little slider bar. So instead of typing a number in, I'm using my little bar to slide it. And then save and check. So that's another way that you can carry out the transformations using the MyMathLab software. Now, the last few problems in the homework are going to test whether or not you really understand what's going on with this. And I wanted to show you an example of it. It says, write the function whose graph is the graph of my parent cube root function, but translated 1 unit to the left and 4 units upward. So I'm going to be looking at taking that parent cube root function. There's no reflections, right? So there's not going to be a negative sign here, nor will there be a negative under the cube root sign. So I'm going to translate it 1 unit to the left, and I know that horizontal translations are within the parent function. And if I want it to go to the left, that means it needs to go this way, right, in the negative direction. So what is going to bring that about? +1, right? What would have to go here in order to get 0? -1, so it would shift left 1 unit. And then 4 units upward is just +4. That part's not tricky, right? It's the left-right that's a little bit more challenging. So you're going to have several like that in order to test your skills with how well you understand how these transformations take place.